So yeah, good morning. If you remember, yesterday we were mostly talking about how to study fluctuations. I mean, all these fields we saw, in particular the density field, it has structures. So just calculating the mean quantities are not enough. So we wanted to see how to characterize the fluctuations, and in particular we concentrated on two statistical quantities, the two-point correlation function and the power spectrum. Then we also talked about how we study fluctuations when we smooth the density field over some scale. So it's like I will put some smoothing window having some size at maybe at the same place but for different realizations, and then I will see how the numbers vary from realization to realization. So that dispersion is crucial. That tells us about the fluctuations, and we saw that these are all connected to the underlying power spectrum of the density field. Today we will ask the next question, that suppose, I mean, it's still, we are talking about statistics, and some of you asked yesterday that are just two-point statistics enough? I mean, the field may actually have more information than two-point correlation function. So again, just remember that we are talking about a random field and we are looking at one realization, and in principle, theoretically, we can kind of imagine that there are multiple realizations of the same field, which are basically your simulation boxes. So for the moment, imagine that I have this universe, big universe, and I have divided that into n points, and each having coordinates x1, x2 up to xn. So what will happen is, as n tends to infinity, the size of the volumes around each of these points will go to 0, and I will recover the continuum limit. So this is the broad idea. So the field delta mx then basically can be represented by a set of n numbers. So I will specify delta m at all the I, where I goes from 1 to n. Of course, again, let me kind of emphasize this. We are not really looking for a method to specify the values of delta for each I, because anyway, those will be random. We really don't want to do that. We want to calculate something which is like this, that what is the probability that I find delta at point 1 between some delta m1 and delta m1 plus d delta m1. And at the same time, I find that over the density contrast at point 2 between delta m2 and delta m2 plus d delta m. This is nothing but I'm building the probability density. So I would like to know this quantity. So if I go to this volume, I have n points. You just tell me what is the probability of finding delta between some value at the first point and delta between some value at the second point, and so on. So if I know this probability, I'm happy. Then I can do all the statistics. All that, then what I can do is I can calculate the mean. I can calculate all the correlations just from this probability. Now, for a general density field, it is not possible to even specify this. So you have to keep on like specifying moments, and you may have to specify infinite number of moments for a general field. Only for specific kind of configurations, this quantity can be like specified. Now, fortunately, if we go at early times, as you know, at early times, the density fluctuations are small, and it's basically in the linear limit. So imagine during CMB or even before that, we are talking about 1 part in 10 to the 5 fluctuations in temperature and so on. Now, it turns out that this initial density field or in the linear limit, it is very well described by a Gaussian random field. So people went and checked in the CMB maps to find evidence for non-Gaussianity, and currently there is no evidence. They're extremely restricted. So if the field is Gaussian, then in general, if there is a Gaussian distribution, you have to just specify two numbers, the mean and the variance, the sigma. In this case, since we are working with density contrast, the mean is 0. So we don't have to worry about that. So then we have to talk about the variance. But remember, this is a joint probability distribution. So you have to just generalize the variance to appropriately describe. So essentially what happens is then this joint distribution is described by, so I'm just writing it fully. Minus half sum over ij, both go from 1 to n, delta m at I, mij inverse, delta m at j. Where mij is nothing but delta I delta j. Okay, it's called the covariance matrix. So this is the basic, this is essentially the relation for a joint distribution of many Gaussian random variables. So you can see there is this normalization part. M is the determinant of this matrix, and this should be n by 2. And then this form you can see has this half delta square by something. But it is not delta square, you have to multiply, the off-diagonal elements also, I and j, when I and j are not equal. And this matrix takes care of that dispersion. If you ended up with only diagonal elements, then you will see that this will be exactly like delta mi square divided by something which are diagonal elements of this quantity. Now, although I have written it as mij, you can clearly see that this is nothing but the 2-point correlation function of xi, xj, which of course for a homogeneous anisotropic universe is a function of only mod xi minus xj. And that is the quantity which appears here. So for a Gaussian random field, if somebody gives you the 2-point correlation function, that is enough. Okay. Then you can work out all the probabilities and any moments, any property of the Gaussian random field of this field you are interested in. Remember, this holds true only for the initial density field at the linear limit. In the linear limit, what we have also seen is all the deltas evolve similarly. Okay, they are all multiplied by this growth factor. So if it was Gaussian initially, as long as it is linear, it will remain Gaussian. Only this variance will change. Okay, it will grow appropriately. When nonlinearity is set in, then there is this so-called mode mixing which happens. Then this breaks down. And that is why for the full nonlinear field, we don't know what this distribution is. We don't know, how far these moments go. We have measured the 2-point correlation function of the power spectrum. People have measured some higher order moments as well. But it is not very easy to fully describe this field in the full nonlinear limit. There are various approximations people use, but in general, it's way more difficult. Yeah. Sorry. I had written correctly then, because it has its n elements throughout. Yes, thanks. Yes. Yeah. Now, few special cases which are interesting. So suppose, let me just do something like this. Suppose you are interested in just one point, okay? And you want to calculate, so you have, remember we had this picture. I mean, we had these realizations of this density field. Okay. Suppose I just am interested in this point. Okay. And I want to ask what is the probability distribution of the density at this point. So going to realization, what you will do is you will calculate the density and then build that distribution. Maybe plot a histogram and see what the distribution is. But from here it is clear that it needs to be Gaussian. So for one point, P of, for example, delta M, just calculated at one point, will be the sigma there, 2 pi e to the minus, may not go so high. So sigma m square is nothing but delta m square. So you will just calculate the variance and that's it. So this is for one point. And similarly for 2 point, you will have a delta m1 square, delta m2 square. And then there will be a cross term, which will be given by the correlation function between these 2 points. Now let us take the next step. What about I go to that point and smooth it with some filter of size x? Okay, so now I'm centered at this point, but I'm smoothing over some filter around that of size x. This is something which we were doing earlier. It could be a spherical top hat filter, it could be something more complicated or sophisticated, whatever you want. Now this delta mx, if you remember, what is it? It is some integral of deltas multiplied by some window function. So in some sense, I mean, not in some sense, it is actually this delta mx is a sum of many deltas. Okay, all the deltas which contribute significantly within that window function. And sum of Gaussian random fields is also a Gaussian random field. You have to just know what the corresponding sigma is. So for delta mx, if I write the probability distribution, it is what? We have already calculated the dispersion. It is sigma when averaged over x. Remember, we did this window function. We said the mean will be 0 if we average over realization, but there will be a sigma. And we calculated that sigma and showed that it is some integral of power spectrum. So this e to the minus now this is going to be very important because we are soon going to use this idea to identify halos, but let me just give you a glimpse of why this is important. Remember, what is this? Again, the smooth density field. I mean, you have this density in your box, which is basically given by this cosmic wave. And what you are doing is you are putting a sphere here and calculating delta. And strictly speaking, then you should take the same point and go to another realization, which will have a different kind of cosmic wave. And you will put a sphere and calculate delta, and so on. Now the values of delta, if you take the mean, it will go to 0. But each of these deltas will have different values, so there will be a dispersion, and that dispersion is this. In fact, these deltas will be distributed in a Gaussian shape. with a sigma given there. Now suppose I want to study spherical collapse. I want to find out the regions which may collapse. Firstly, not all spherical regions collapse, because we saw that it has to be overdense at least for collapse to happen. Remember, the delta initial has to be positive, if you go back to our spherical collapse discussion. Of course, what will happen is some of the case delta will be positive, some of the case delta will be negative. In fact, they will be symmetric because you have to make sure the mean goes to 0. But then we are interested in seeing that whether this delta, if I evolve linearly, whether it crosses that value. Remember 1.686, something we calculated, that if we evolve linearly, when it collapses, it should be 1.686. Now, higher the sigma, better chance of finding those large values. Okay. Okay, there will be many places which will also have very large like negative values of delta under dense regions, but that's fine. They will go to voids. I don't care. Okay. But I will find lot of places which will go to, which will probably collapse. I will make all these things more quantitative soon, but this is the idea. So this is where this Gaussian distribution becomes very important. This tells us what is the probability of finding these regions which are likely to collapse. Okay. One more quantity of interest, that is delta k. Now delta k is the Fourier transform of delta. So essentially that is also a sum of many Gaussian random fields. Okay. So this also itself is a Gaussian random field, except this has an interesting property that delta k1 and delta k2 are uncorrelated. It's like proportional to delta d k1 plus k2. Okay, or if you put a star, then it will be k1 minus k2, whichever way, both are fine. So what it means is that the covariance matrix of this quantity is diagonal. Okay, it does not have any off-diagonal terms like the real space counterpart. And the diagonal elements are nothing but the power spectrum. Okay, because that proportionally constant will have a power spectrum. So you have to, I mean, when you actually implement this in a code where these k's are discrete, so you have to worry about how to deal with the delta functions, but these are all done. This is very important, for example, for the simulations you are doing. So if you again remember, when we were setting up initial conditions, what did we say? You set up this grid, and maybe at each point you put a particle initially. If you leave them, they won't move because it's all symmetric. So you have to give them some initial small kick. That we will give using linear theory. And in the linear theory, we saw how much kind of displacement we have to give. That was given by Zeldovich approximation. And that displacement was proportional to some gradient of psi naught, where psi naught was some scaled potential. So this is the displacement you have to give. And this psi naught is of course also related to, it was proportional to the delta as well with a minus sign. So these are all there in your notes, and we have discussed this. So we know that we have to give displacements, but then we have to give displacements to, in your case, 64 cube particles. Those are huge numbers. So you need to know those numbers. So how do you actually calculate this psi naught at 64 cube points? What you do is, you know that this psi naught, which is also proportional to delta. So if delta is a Gaussian random field, this psi naught go to Fourier space. So then what happens is psi naught basically becomes delta by k square. So this psi naught is also a Gaussian random field. Moreover, in the Fourier space, so Gaussian random field, you need to specify the dispersion or the sigma. In the Fourier space, it is diagonal. Okay, so different k modes are not correlated. So that is it. So what you do is so you have to choose what power spectrum you want to work with. So power spectrum will be given by all the cosmological parameters. So you have fixed the cosmological parameters that sets the power spectrum. The moment that sets the power spectrum, you have a control on sigma. Now you have to just generate a random realization of this Gaussian field, which has that power spectrum which you want. And if you change the seed, it will give you different realizations, but all having the same underlying statistical property. Okay, so those are your simulation. And that will set this value of psi naught. So you will generate in the Fourier domain, then do a Fourier transform, and then possibly add that displacement in the simplest case. You can now make it more sophisticated. You can say that I want to go to the second order Lagrangian perturbation theory, make it more accurate. So those are details, but this is the basic idea. And this is where the Gaussian random field and the power spectrum enters in your simulation. So if you can access the initial condition file, first of all, you will see that the particles are almost in a uniform grid, but they have moved. And if you calculate the power spectrum, they will be to a very high degree of accuracy consistent with the linear power spectrum. When it evolves, when you go to lower and lower redshifts, then it starts to deviate from the linearities. So all these things in principle you can see from the simulation you have run. Okay. Yeah, and there are, generating in Gaussian random fields, there are lot of subtleties which of course you have to take care of. For example, you have to ensure that delta in physical space should be real. You don't want to end up with imaginary or complex density contrasts in linear space. To do that, you have to make sure that constant, remember delta m star of minus k is delta m of k. All these constants have to be satisfied. Okay? So all these things are done while generating the initial conditions in the codes you are using. So these are basically details and subtleties you have to take care of. Now you can already see, as long as we are working with this, like the linear field, it is good. It is all Gaussian, everything is given by sigma and the power spectrum. And we can probably work out various things analytically, which we will do. So this gives rise to the concept of linearly extrapolated field, which you have already encountered. Extrapolated field. So what you do is you evolve the field using linear theory. You don't worry about whether linear theory is valid or not. Okay, you keep on evolving till redshift 0. Okay, so that is called linearly extrapolated field. Of course, when the linearity breaks down, this won't give you the true field, but it will give you some linear approximate version of that. We have already used something like this while discussing spherical collapse. We saw that in spherical collapse, the density, the spherical shell expands, then it basically collapses, and during collapse, it has a density contrast of the order of 200. But we could still evolve the delta linearly. That is, we can always do. And we found that that also has some significance, because when that delta hits some critical value, we know the collapse happens at that point. So that is where we use this linearly extrapolated field. I had shown you a plot of power spectrum in a slide in the first lecture, which looked like this, with all data points put in. This was also something which was linearly extrapolated. So what was plotted was the linear power spectrum at redshift z equal to 0. So clearly at z equal to 0, not everything is linear, but what was plotted was the linearly extrapolated field, linearly extrapolated power spectrum. Okay, so that is the idea of linearly extrapolated field. So if we do linearly extrapolated field, again, let me just write for completeness sake. So any delta calculated at some z at some value k will be d plus z delta m at z equal to 0 k, because k modes evolve independently. And from now on, this I will just write it as delta mk. So whenever I write delta m without any mention of z, that will be at redshift equal to 0. And that is the convention which is often used in cosmology. D plus at z equal to 0, the way we have normalized is 1. So this is correct. And then power spectrum zk is nothing but d plus square of z power spectrum of k. This is also at redshift equal to 0. And you can do this thing for all the quantities of interest. For example, sigma m square of z smoothed over some x is also d plus square z sigma m square. Sigma m will be d. These are all linearly extrapolated quantities. Yeah. Yeah, there was some cheating there in the sense the observational data points were kind of corrected to bring it to, to correct it to like match with the linear spectrum. So the observationally you would have found the actual nonlinear power spectrum, but then we know what is the mapping between linear and nonlinear. So it was done in this way. Remember that plot was mainly for visualization. So that plot is never used for actual quantitative analysis. So for quantitative analysis, people would have run the proper simulation, calculated the nonlinear, whatever, if needed, the nonlinear equivalent of all the quantities, matched with the observations, which would have also had nonlinearities. And then when they know that they match, they know from the observed power spectrum how to bring it back to the linear power spectrum. And that is what was plotted. Okay. Yes. In this picture, it will be encapsulated in both delta k and the power spectrum. So power spectrum at z equal to 0, we know the shape is like this. Okay, so that already knows basically. So what happens is essentially here, this power spectrum, we will write it as the primordial power spectrum times t square k. Okay, it has the transform. Exactly, so it is included. This is z equal to 0. So z equal to 0, this might be actually set up very early, but it has gone through this transfer function. So it is all included here. Okay. Now we are in a place to talk about halos. Okay. Just using linear theory and spherical collapse and Gaussian random fields. So let us see how it works. So let's be just quantitative once more. So let us imagine that I am at some very early redshift. Let's call it Z initial, which is larger than 1, where things are guaranteed to be linear. The perturbations are extremely small as you want. You just go early in redshift. And I have this field, delta M, Z initial, X. And essentially, it was all given by this power spectrum at Z initial case. Now let us take this field and smooth over some scale x. So let us use a spherical top hat filter just to make it clear. Because when we did spherical collapse, we said there is this spherical region which encloses some mass m. Okay, so this was a kind of sharp-edged spherical region which has a clear radius. So that is the spherical top hat filter in the real space. So you smooth over x. So basically what I have is delta m smoothed over x, Z initial at this point x is nothing but this we did earlier, d cube y delta m Z initial calculated at x plus y and some window function of y. So you will use the appropriate spherical top hat form. So this is my field, okay, smoothed over x, some spherical region x. Now we know that this will evolve as long as I am in this linearly extrapolated regime. So what happens is delta mx, so I am just evolving it linearly. At any redshift x will be nothing but d plus at that redshift divided by d plus at the initial redshift times delta mx z initial x. Also, this region of radius x will have a mass. That mass will be 4 pi by 3 a initial x cube. This is the physical radius times rho matter calculated at z initial, right? This will be the mass inside. But remember, I'm at very early times, so the perturbations are really, really small. So I can replace this rho matter by rho bar, okay, because that will introduce an extremely small correction. So rho m bar z initial times a initial cube, that will give you the rho m bar today. Okay, is everybody convinced? Rho m bar z initial times a initial cube, what do you think it will be? What is rho m bar at some a given in terms of rho m bar today? 1 by a cube, and you are multiplying by that same a cube, so you will end up with rho m bar today. So this will be 4 pi by 3 xs cube rho m bar 0. This is just a consequence of the fact that we are working in co-moving coordinates where this a is scaled out. So you end up with something which is basically the density today. Okay, that's also called the co-moving density. So as far as this picture is concerned, then x and m, there is a one-to-one relation. So every region of size x, I can basically ascribe a mass to it. And that is the mass which, if conditions are favorable, may collapse. And that is what we want to look for. Now let us say, so this is the smoothed field at redshift z. So starting from the initial one, I have come to this point. Now it is actually simple. So this is the smooth field. So it has given me the value of something average, the value of the over density contrast averaged over these radii of x. So I have to just find how many such points have crossed the threshold. Okay. Every point which has crossed that threshold at redshift z would have collapsed. And the mass would be this mass. So it is, I mean, as simple as that conceptually. So basically what it means is that I have to just look for places where delta mx z x is greater than delta critical. Delta critical is 1.66. That 1.686, that comes from spherical collapse. So while doing spherical collapse, what we saw is that the actual radius, so you have a spherical region. So what happens is the spherical region, if it is overdense, the radius versus some A or Z, whatever, it increases and then goes down. So initially it was increasing with the expansion. Then because it is overdense, it starts to slow down compared to expansion. So the expansion might be going this way. It slows down, turns around and collapses. But of course, it really doesn't collapse to zero because all this non-tangential motion takes over. So it probably is from somewhere here, it is some violent relaxation and reaches some equilibrium here. But now we said that let us take the initial conditions and evolve the density linearly, okay, which won't give you the true density. Now, if you do that, what you can show is that at the point of collapse, that linearly extrapolated density will have a particular value for matter-dominated universe. If you have lambda, it changes a bit. So that is the critical density for collapse. So that is 1.686. Yeah. Yes.
Has enough density to collapse. Right.
Correct.
So suppose within this sphere, if there's a smaller sphere that has already reached the density and it has already collapsed, do we need to exclude those cases?
I will come to that. Okay. For the moment, let us just take that. You imagine that you are interested in only 10 to the 11.5 solar mass halos. Fine. So you then calculate the x. You just smooth the density over x and you say that I want to see at redshift 1.736 how many of them have collapsed. So you will calculate this quantity at that redshift. X is corresponding to that mass you are interested in, and find out the regions which have crossed 1.686. So those details will be addressed very soon. So this led to this concept that I can calculate the fraction of mass within collapsed halos of mass m at redshift z will be this, of mass greater than m. So let me write this expression and then let us see if we understand this. What we are saying is I want to calculate the fraction of mass within collapsed halos having mass greater than m at redshift z. I know that at redshift z, if the smooth density hits 1.686, it is collapsing at that z. Okay. And since I'm talking about smoothing over x, this x is related to the mass by that relation. Suppose at the same redshift, I look at points which are larger than this collapse density, then they would have collapsed earlier, and definitely because I have smoothed over this x, they have to have at least that much mass, or they could have had more mass than this. That's why they collapsed earlier. So keeping the, yeah. This is, yeah. So ideally, all these things are done in this ensemble sense. So you are as if doing it at one point for every realization. and seeing what fraction is collapsed. Then you use ergodicity to compare, convert it into some kind of our universe, different points. So yes, so now this means is I have kind of averaged over all points in the universe and found out what is the fraction of mass that has collapsed. Okay, collapsed to within halos of mass greater than m, and that is given by this Gaussian function, because all these points have densities larger than the critical density, so they would have collapsed. So the ones, the delta mx, which are exactly equal to delta c, are collapsing exactly at this z. Others have collapsed earlier. Now this you can work out analytically. So I mean, analytical in the sense, integral of an exponential will give you an error function. In this case, a complementary error function. So this will give you half this complementary error function delta c by root 2 sigma m of zx. But then sigma m of zx is what? It is d plus times sigma m today. So this d plus I can take and combine it with delta c. So this I can write it as half error function. I make delta c, I write something called delta cz, where delta cz is nothing but this delta critical by d plus z. Okay, this is all identical. Yeah. Yes. Yes. And delta cz is 1.686 divided by the growth factor. So here what we were trying to do is we were trying to see whether the density field has enough dispersion that it crosses delta c. The density field at redshift z, whether it has enough dispersion crosses delta c. This is equivalent to saying whether the density field at redshift 0 has enough dispersion to cross delta c by d plus z. This is equivalent. So in one picture, what is happening is you have this density field and you are looking at this threshold. So that is one way. Other way, and then the density field probably as the redshift increases, this density field increases and it becomes easier to cross that threshold. The threshold remains the same, the density field increases. This is the picture. What I'm replacing it with is that the density field remains static, but the threshold decreases with redshift. Okay, these two, because all are in the linear limit, all are growing by the same factor, these two will give you identical numbers. And that is essentially this. Which one? Which one? 1.686. Why do you say it has to remain the tail of the Gaussian? So if sigma m is much larger than 1.686, okay, then it's all within. So you will have a lot of collapses there. So it will now depend on your calculation of sigma m. Okay. And we will see how these things evolve with redshift. Now there are some subtleties here. So just to complete this picture, what we can also see is we have already written, we have already shown that x and m have one-to-one correspondence. So I may as well write this as error function of delta cz divided by sigma m of m. So whenever I write sigma m of m, you have to mentally first convert m to the corresponding x and then put those spheres. Okay. So yeah. And now this whole thing has become independent of that initial redshift. So as long as you start at a redshift which is very, I mean, where the perturbations are really small, this whole thing goes through. However, now there are subtleties which we have to worry about. First point is, suppose I take the limit m going to 0. Okay. So that would mean that I am starting with halos. So this is, remember, these are halos having mass greater than m. If I take m going to 0, that means I am talking about all halos in the universe. And if I take the mass going to 0, it should contain all the dark matter because there is nothing outside. Now, if you take this m going to 0, you will see that this quantity F collapse limit m going to 0 greater than mz goes to half because of that half sitting outside. Now this is basically violating like mass conservation. It's not normalized clearly properly. Okay, it should go to 1 because all dark matter should, or all matter should be within halos if I take the mass m going to 0 limit. This has to do with some of the subtleties you were asking about. So what happens is, here I have integrated over densities above delta critical. It may happen that there is a density which is less than delta critical. Okay, so you have some sphere which is which has delta x less than delta critical, but it is actually sitting in a much larger or a larger sphere which has value the average density greater than delta critical. Then what will happen is this larger sphere will collapse, and within that this one will also collapse. So clearly it doesn't mean that if the delta is less than delta c, it cannot collapse. It will depend on what is happening at other scales also at the same point. Now this was missed in this simple calculation, and it turns out that since you have missed it, it actually contributes to exactly factor half. And I will come back to this point again soon. So for the moment, what we will do is we will just replace this number, we will just multiply by 2 and say that F collapse at z greater than m is complementary error function of delta c at z by sigma at z equal to 0. This calculation was first done by Press and Schechter in the 70s. And all the formula we derive, I mean, we will reach something called Press-Schechter mass function. But they had this famous problem of factor of 2. Okay. Now, I want to know something more. What I want to know is the number of halos per unit co-moving volume per mass range. So dn will be the number of halos within a mass range m and m plus dm per unit co-moving volume. So this is the mass function, and I want to know its form. Now if I write the same F collapse in terms of the mass function, it will be what? So suppose I integrate over all halos having mass greater than m. This is the number of halos per unit mass above m, and then I multiply by mass. So this is the mass content within halos having mass greater than m per unit volume. So this is the density basically, and that I divide by the average density. Now I have one expression for F collapse here, another expression for F collapse here. So you have to do some manipulation, and this will immediately give you the form for dn/dm. So I'm not doing this, but I will write the final form directly. It will be dn/dm equal to root over 2 by pi rho m0 by m, then d sigma m by dm, and then delta cz by sigma m square m, and then exponential of minus delta c square z by 2 sigma m square. This is the famous Prayush mass function, which many of you would have seen or even used in your calculation. Just appreciate that this was derived, I mean, modulo some subtleties, this was derived almost analytically by using essentially three ingredients: linear perturbation theory, spherical collapse, and Gaussian random fields. Okay, you really did not need to go into like fully nonlinear theory to do this. And in that, now currently, I mean, we know that we can calculate the same mass function as you will do from simulations. It does not match the simulations too well. I mean, when it was derived, the simulations were very low resolution and people could see that, okay, it's roughly matching and people were happy. But as simulations became more and more sophisticated, it's clear that it doesn't describe, I mean, it doesn't match the simulation results that well. But the qualitative features it describes still holds. Okay? So we still use this to get insights on like evolution of formation of halos, evolution of halos, how the mass is how the number of halos is distributed across mass, how they evolve, and so on. Knowing full well that the actual like quantitative numbers could be very different from what is given by Prayush. Now let us try to understand what it says. So I will leave this here, but then go to the other side and continue. So firstly, you see there is an exponential sitting there. And within that exponential, we have a delta Cz and some sigma m. So then we can set up a characteristic mass scale, let us say m star, such that sigma at m star is equal to delta C of Z. This, in some sense, is the typical halo forming at redshift Z. In other words, what is happening is when I average this density field over this mass scale, I will see that within 1 sigma, or at 1 sigma, I am hitting this collapse threshold. Okay. So these are typical halos which are collapsing. So smaller mass, also remembers masses which are smaller. So if m goes down, sigma m goes up. So the dispersion is higher at small masses. So as a result, it becomes like easier for small mass halos to collapse. So you will see the mass function to be like it has more halos of smaller masses compared to larger masses. Now for m less than m star, the exponential term is kind of like roughly equal to 1. It basically follows, the mass function follows almost like a power law, not exactly, so you can call it a quasi power law. So it follows a kind of power law form. And at m greater than m star, basically the exponential takes over, so you have an exponential cutoff. Often this DNDM is written in a slightly different form, and let's do that. dn/dm is also written as root over 2 by pi. The first part remains same, rho by m, and then you put a d ln sigma m dm, and then nu e to the minus nu square by 2, where nu is nothing but delta Cz by sigma m. So what happens is, imagine you are smoothing over larger and larger scales, the dispersion is going down. So you will find it very difficult to get a region which can cross this threshold. The form of exponential comes because of Gaussian random fields. If you track back, it's because high density peaks are extremely rare. Okay, so what happens is, as sigma goes down, so this brings me to this point. So this nu, I mean, it's written, just that one is written in terms of nu. Nu tells you how rare or how far away from sigma you are for the mass to collapse. Okay. So if nu is large, which means sigma is small for the same redshift, that means you will find it difficult to collapse. Okay, you will probably hit the exponential cutoff. And vice versa. When nu is small, which means sigma is high, so probably mass is small, then it is easier to cross, given the same redshift. Okay.
This is an intuition for the power law behavior at low mass?
Yes, okay, yeah. So what happens is, so if at low masses, so for example, at low masses, if you take sigma to be large, then what happens is the nu basically becomes small. So you are at that proportional to nu regime. So other way of looking at it is this. So suppose I take this thing which I was also discussing last time. So suppose I say that power spectrum is k to the n. This n is not that initial, the primordial value. For the galaxy scales which we are interested in, it's probably somewhere at minus 1.5. So if you do this, what you will be able to show is that sigma m square x goes as x to the minus n plus 3, and m goes as x cube. So sigma m square m will go as m to the minus n plus 3. So let me put sigma m goes as n plus 3 by 6. Okay, so I have just instead of sigma m. So now if you do, so d ln sigma and dm will just give you 1 by m because we have taken a log here. So it is 1 by m square, and nu gives you some power law of m. Okay. So for minus 1.5, n equal to minus 1.5, this will be something like this dn/dm will go as something like m to the 1 point, let me, I have done that, 1.75. So these are the typical numbers. And then you hit m star and it falls exponentially. So if I plot it roughly, so dn/dm in log scale versus m, both are in log scale, you will see initially it does like this, and then at some point it just starts to fall. So this will roughly be m star. Yeah. Okay, the approximation under which we are working, it will go on forever because we have put pressure to 0. So dark matter or whatever, the collisionless matter will form structures to smallest and smallest scales. Of course, at some point we know that is not true. I mean, dark matter is a particle and it will have interactions no matter how small it is. But as long as we are at cosmological scales, yes, we don't have to worry about that. But yeah, theoretically, it will just go on producing more and more halos. And if we integrate now this mass function from m0 to infinity, that will be all the mass in the universe. Now what happens is, as I said, this gives, So even from simulations, when you get the mass function, you will see it has somewhat similar, though since your simulations are very low resolution, you may not be able to see this power law part very prominently. You might be most of the time in this exponential tail. People went ahead, and then you can make this calculation more and more sophisticated. You can say, why stop at spherical collapse? I mean, can't we generalize it? And people went and did ellipsoidal collapse. So what it does is this ellipsoidal collapse changed this barrier, okay, this delta C, and that, remember, that was like a constant value, okay, it did not depend on initial condition or mass or anything. If you do ellipsoidal collapse, it picks up some shape. So that changes the form of the mass function. But again, the basic idea still remains the same. Okay, lot of small mass halos, exponential cutoff at high masses. One axis. In principle, yes. Okay. Yeah. See, I mean, even these halos have angular momentum at the end, because you have put in lot of random motions, and you don't know. I mean, at the end, it may have angular momentum. It's just that what we are doing at this level is that we are saying all properties of the halo are entirely determined by the mass. But if you go to your simulations, yes, halos will rotate and so on, and you can then start segregating. Even at the same mass, are the properties different based on other quantities. Yeah. But even spherical collapse, no matter what you do, finally you will find, I mean, that is why it's called mass function. You will write the expression in terms of masses. So here our intrinsic assumption, and that I will use even in the next lecture, is that all properties of the halo are given by mass and the redshift, of course. It may not be correct, even with the same mass, depending on where it found, what is nearby the environment, it may be different. But
realistically, is that momentum important?
It affects galaxy formation. Okay, but DNDM is reasonably, I mean, you can, yeah. So, okay, or let us take a step back. It depends on the problem you are trying to address. Okay, so if you are really looking into galaxy formation, star formation, and things like that, the disk forming, it may matter. Okay, yeah. But the kind of things we will talk about at the level, it won't. Yeah. No, it is slightly more complicated. Yes, yeah, it is difficult to give a closed form. So at the end, they will give a fitting formula, which will be having this shape. But what will happen is delta critical will be replaced by some other value, and there will be other numbers sitting here and there, basically. So yeah. Yeah, basically, okay. So let me go to the next point now. So as I said, the ellipsoidal collapse is also very popular, and that is called Schett-Terman mass function. Correct. Because the ellipsoidal collapse, just from ellipsoidal collapse, it's very difficult to just find something in the closed form. So they will have tuned some parameters there to match the simulations, and then those parameters also evolved with simulations. So Schett-Terman's parameters are not what is probably used later, and so on. Let me quickly give you the idea of, now you can ask this factor of half, okay, we did it, we just put it by hand. Now, is there a better way of solving this problem? And indeed there is, okay, and that was solved by various people in the 90s, okay, Dick Bond, George F. Satiew, and many other people. What they did was very interesting. So I won't do the calculation, but give you the idea. So what you do is, you go to your simulation, imagine you have this volume and many replications of it. And what you do is, you go to the central point, okay, and you start by drawing the largest sphere you can. So when you do, when you draw a very large sphere, you can easily understand that this sphere, if it is very large, it will, the density within this sphere will be equal to the mean density of the universe. So the delta, if x is large, will essentially be 0. So let us try to then plot something. So I am plotting here delta mx at some given point versus x or m, except they are increasing this way. So I take the largest x. I know that I will be somewhere here. Okay, I will start probably from 0. Then I draw a slightly smaller sphere. I will get some value. It could be positive, negative, I don't know. Okay. And then a smaller one. Okay, again, it may do something like this. So this looks like some kind of a trajectory as a function of x. Okay, remember when I say trajectory, there is no evolution happening. It's all happening at the same redshift. It is happening as a function of smoothing scale. Then you go to another realization and you do the same thing. You will get another realization of this curve. And maybe in the first realization, you are sitting in an overdense region, so it went up. Here, it has gone down. And then there could be other realization where it goes up, then comes down, goes up, and so on. Okay. So you can build these trajectories. Of course, these trajectories, as we said, they will start from 0, because if you put a large enough sphere, when it goes, the size goes to infinity, there are no fluctuations, and then you pick up fluctuations. However, suppose you are at some particular scale and you are looking at all the realization, you know that the probability of finding a value between some delta mx has to follow the Gaussian distribution, right? This is our Gaussian random field calculation. So after you have drawn all these trajectories for many realizations, at every point they will be like centered around 0, so that is the mean, and the dispersion will be given by sigma m. And we have seen that sigma basically decreases with m, which means as we go along this side, the sigma or the dispersion will increase. Okay. So as you come to smaller and smaller m, you will see more and more trajectories going this way. So here there will be tight, and it will all go like this. So these are the trajectories. Now what you do is, now let us draw just one trajectory and see what happens. So this is that, let us say this is one trajectory. And I have drawn this because I'm interested in halos, so I am saying that it is probably, let us say, over dense regions. And there are equally probable trajectories which will go downwards. Now remember this, I said the density field we will calculate always at redshift 0. And to understand halo collapse, we will just shift the threshold. Now, if we are very early redshifts, your threshold is what? Delta C 1.686 by dz. Very early redshift, d is small. So the threshold will be very high. Okay, so at very early redshift, you are probably somewhere here. And there will be no halos. Okay, so if you go to your initial condition field, run a halo finder, it will give 0. There is no halo. Now you slowly start decreasing this. So I'm just removing unnecessary stuff because I want to point out a few things. So suppose at some redshift Z1, the threshold has hit here. Okay. So then what will happen is, at that point, a halo will form, which will have this value of x or this value of mass. And you can understand, because the dispersion is like larger at smaller m, you are more likely to form small halos first. Then as redshift increases, this threshold keeps decreasing. As the threshold keeps decreasing, you see this m, the equivalent value of m where the threshold is crossed, is increasing, but it is increasing continuously. That is like the halo is accreting mass from surrounding. Its mass is constantly increasing, but slowly. So there is this accretion phase. Now it goes down, so it has probably reached here. This is the mass at some redshift. Then at the next redshift, it comes here, let us say. So now a halo of this mass will be formed because it has crossed here. So what will happen is, in a small redshift interval, the halo mass will jump from here to here. This is called merger, okay, which means, of course, we are tracking just one point at a time. But what has happened is, from somewhere nearby, another halo has come and these two halos have merged and formed a large halo. Okay. So this is merger. So this is like one jump in the halo. So you can see, and so that is one part of this. So this picture clearly has a lot of kind of insights built in. Also, Bond et al., what they did was they interpreted, or they could map this problem to a random walk or a Brownian motion problem. So these are like different realizations. So these are basically different random walks. And given a barrier, you just have to find when does this trajectory cross that barrier first time. Okay. So that becomes a first crossing problem, which is a solved problem in random walk. So they could just use those results. And when they did that, they recovered exactly this form with that factor of 2 properly accounted for. Okay, that went away because it automatically accounts for something like this. So for example, this region has delta C less than 0, but it can be part of this halo. So all these things, otherwise we would have just discarded these points saying that they don't have enough delta critical. So all these cloud in cloud problems and other things were solved. And then people realized that you can use it for understanding merger. So this is I drew a trajectory and showed you how it happens. But what you can do is you can analytically calculate probabilities of mergers. So you can say that what is the probability that a halo of mass m had a progenitor of some mass something m2 at redshift earlier z2 or something like that. So you can basically formulate very precise questions regarding mergers and work out the corresponding probabilities and numbers from here. This also tells you that structure formation is hierarchical because small halos tend to form first, just because sigma m is larger at small m. And as you go down, then they merge and form large halos. And as the universe expands, this threshold goes down and you will form larger and larger halos. You can also see that small mass halos, which could be rare at early redshift, difficult to form, could be very easily formed at a lower redshift. And high mass halos will then become rarer. Okay, yeah.
To look at the probability of mergers, one has to look at different snapshots in time, right? But they would
yeah, in this case, different barriers in this case, because this density is frozen today and the barrier is going up and down. So you have to ask that what is the probability that it first crossed here and second crossed at some, when you say other redshift means some other barrier and so on. So all these joint probabilities have to be worked out. So in principle, this can be worked out. So this formalism is called excursion set. It's a very powerful formalism. Of course, at the end, what it gives is still approximate, but it contains the insights which are very useful. And people have gone ahead and modified this, made it more sophisticated to make it work, maybe try to match with simulations better. But it is still an analytical handle. I mean, if you want to do accurate mass functions, you need to go to simulations. There is no other way.
Aspect of the redshift, like we had a particular realization.
Yes.
We are changing the redshift towards today, and then the merger etc. happening pure of the redshift artifact.
What do you mean artifact?
How should I say? Like for a particular Z, nothing merger etc. is happening. As long as you are changing the Z, then only.
Yes, so at some redshift, you have a snapshot. You have this hello, that hello, that hello. Okay, as you evolve, what will happen is two hellos will come together, come close and merge. That doesn't mean every hello in the universe will merge with something else. Okay, I mean, so.
If I keep the snapshot itself and just trace the hello, then also they would merge probably due to gravitational effect.
No, what do you mean? Snapshot is one redshift. Yeah. It's static. It's not moving. So at least you have to move to the next time step, right? Only then. So merger is a time dependent. So something has to come and merge. Okay, snapshot is literally snapshot. Yeah, I'm taking a picture of you and looking at you. You won't move in that picture. Okay. Okay, yeah, then I have to take more pictures of you if I want to see you moving to somewhere else. Okay, so that will be like the evolution. So as you can see, at earlier times, mergers are more common, and small halos like tend to merge more. This is a very qualitative statement, and later mergers become like less and less common. But all this is really qualitative. When you have to really work out the quantitative details, and this common and less common could also be relative in some sense. Okay, but yeah. Remember, depending on redshift, the mass scales themselves are changing. See, this M star, the typical halo is different at different redshift because your threshold is constantly changing. So something which is very rare at early redshift can be very common at low redshift. Exactly. So delta CZ has a D plus hidden. Okay, so M star constantly changes. So M star typically will be lower at higher redshift and kind of increase slowly. So for example, 10 to the 12 solar mass halos today will be very rare. 10 to the 8 solar mass halos will be all over the place. But if you go to redshift 10 or something, even 10 to the 8 solar mass halos will be extremely rare. Okay, and 10 to the 12 you cannot even imagine at those redshifts. So it all becomes very relative. Yeah.
This conclusion from that is structure formation is hierarchical.
Yes.
Can be drawn directly from the observation or the calculation that this has a negative index in the power law, or it has to have its mergers also factored in.
Yeah, okay. Both are connected. Yes. The fact that the dispersion is higher at at small m already tells you that lower halos will form first. Okay, but then, I mean, if you now ask the next question, that what happens to the lower mass halos as the universe expands? I mean, do they just remain as they are? That is where the merger comes. In fact, many of these lower mass halos will keep on merging and form the large mass halos. There will be large mass halos which may be forming for the first time also. Just that is the first time it is collapsing. But they may come also from mergers, and all those probabilities can be calculated from here.
Yeah. That has to depend on a bigger calculation.
Exactly, of all these trajectories, exactly. Or then otherwise you go to simulations. Now these kind of calculations are very important. I mean, suppose you started, when I discuss gravitational wave events in the next lecture, I can allude to some of these. I mean, imagine that some star formation has happened, and maybe a binary has formed and it is waiting for it to actually merge. I mean, now I'm talking about stellar mergers, the compact object mergers for the gravitational wave. But by then, suppose the halo, the galaxy merges with some other galaxy. Now what happens to this event? Okay, I mean, I don't have a clear answer. I mean, will that get disturbed or it still continues or so on? But if a new halo is formed and it remains like unperturbed, it does not merge for billions of years, then there is no problem. So these mergers can play a role. So we know it plays roles in star formation, for example. So when people try to model star formation in great detail, they have to account for the fact that a halo which has formed will not live forever. And if you have merger, you can induce further star formation. So all these things can play a role in any like tracer of star formation which you eventually want to understand. And of course, these mergers are important for your the central black hole growth as well. So, yeah.
So I need to, I'm understanding one merger scenario.
Yes.
Here, this is a situated at some point, and I'm increasing the radius and I'm taking the average.
Yes.
Right. So
the radius is increasing this.
In this,
Yes.
in this that direction. Right. So when the radius is the largest, that is the average is 0.
Yes.
So in principle, these fluctuations are random. That is
Yes.
right. So at some point when there is a mass collapsing happening at
Yes.
some point.
Yes.
So that is a particular mass that can be distributed somewhere else. I mean, this is like small
Yes, it's
masses.
coming from somewhere. Yeah.
So whenever the threshold comes down to having 2 peaks within the threshold, that is
Yes.
like 2 collapsing situation, but those are at different sizes because these are like 2 M's. That is
Exactly.
X.
So it is at the same point. So how am I drawing the trajectory? I'm sitting at this point and constantly decreasing the radius. Okay.
Yes.
And what I'm seeing is at that point, this mass had crossed the threshold at some z, and as I go to z minus delta z, it jumps. Okay.
Yeah. So about the jumping part, that merger you are saying, but this is like a statistically averaged quantity. So it can be that this over density, like the collapsing region, is somewhere else, and the other collapsing region that I have found is somewhere really far away. But since I have just averaged it out, I can see in a single plot. So it might not really merge, right, in that sense.
No. So here there is no, I mean, there is a jump in mass. Okay. And that has to, I mean, so if in a small time shift, if I'm getting a mass which is of similar order of the original mass, that means there was some other halo nearby, right? It cannot be that I am this massive and I'm a halo and I'm getting equal amount of mass from somewhere else. So that must also be an halo. Okay.
No,
this can even be larger.
I'm more concerned about the positions. Like for example, since
yes,
this is an
so now,
average,
yeah. So now there's a conceptual issue here. Okay. So what we are doing are realization averages. Okay. So I'm sitting at the same point. And of course, this is one. Now what has happened is at this point, I have seen at this center, the mass has increased. This picture does not tell me whether there was a halo here or not. Okay, that is, I am like inferring that my mass has increased, meaning increased by like 10 to the 10 solar mass. So it has to be, and in a short time frame, so it has to come from some halo nearby. I cannot accrete 10 to the 10 solar mass in that small amount of time. Okay. So this one won't tell you. And I will then go to next realization, again do something. Again, if a merger happens, I don't know from where it came. Now this is this realization problem. Okay. If I now want to do it here in the same volume, you could have done that. I will do this trajectory here and I will go to the next point and do the trajectory and so on. In principle, you can do that, but there is a big risk. When I was going from realization to realization, I could assume that each of these trajectories are independent of each other. When I do it in the same volume, I cannot do that. So statistically, I can get all these probabilities and everything nicely from this picture. When I try to implement this in a simulation box, it can become very tricky. So you can say that I will look at my initial conditions, find out all the peaks and say a halo has formed here, halo has formed here. There is a big risk because all these are done assuming independence of trajectories and that may not hold. People have implemented this, but they had to be extremely careful as to how to deal with nearby points because they will be very severely correlated. So if this is a trajectory, the nearby point will almost follow the same trajectory with some differences. Okay, so that is the, but unless you do that, unless you find out the trajectories of all the nearby points, the question you are asking cannot be answered. That if the halo has formed, where did that halo come from? If the halo has merged, then I have to do this trajectory at every point. And the difficulty of doing is this. So at that point, my suggestion is run a simulation. Okay, so, and you can track the particles and see the halo will be formed. This is more to get insights. Okay, so the kind of questions you are asking, why does like the simulations will show you that mergers are very prominent at early redshift. Why is this happening? So that insight will come here. Or maybe small halos are forming first, and this you can see from simulation very easily. Why is this happening? So the insight will come from here. Okay, so that is the balance you have to strike between analytical calculations and the simulations. Okay. Okay, maybe I can stop here. I wanted to do the bias, but that will take 10-15 more minutes. I can go to the next lecture and then, yeah.
Are there any more questions? We have had several. Okay.
Yeah.
So in this picture, suppose I have two halos mass M1 and M2 at some redshift.
Yes.
Then as you decrease the redshift value, suppose this happens and the two halos merge.
Yes.
So is the mass of the merged halo actually M1 plus M2 or something else?
It is roughly M1 plus M2. I mean, even if, see, if they are merging, so there could be some disturbance, some particles picking up large velocities and going away, but that is minor. It will be M1 plus M2.
But then how is the possibility that a larger halo has collapsed,
Yes.
but these two smaller halos were lying embedded within that region? Where is that possibility accounted for in this
Yes.
picture?
So that is, so what will happen is, imagine, so basically what you are talking about is subhalos, essentially. So what has happened is, in this case, of course, this is a halo, but there could be many other points which have like crossed the barrier at smaller masses. And we know that they have also collapsed. Okay? So within that, you can have small subhalos sitting. Right. So that it is included in this picture, basically.
So as we go to smaller redshift,
Yes.
how do we know, in this picture, whether the two halos I was talking about, where is the fact that they have merged or whether they actually got embedded into a much larger halo? How is that distinguished?
What do you mean? Two halos merged, and okay, what you are saying is you have a large halo, and yeah, okay, that is more difficult in this picture because there you have to know where these halos came. See, here I know that this halo picked up some mass from somewhere. It doesn't tell me that, then I'm inferring that halo had some mass and got merged. Yeah, so that part may not be clear as to whether something is embedded within a big halo, how many of them are embedded, because see, I'm doing a excursion set at this point, okay? And maybe you say that there is a halo formed, but actually there are subhalos here and here. But for that, I would have to do excursion set at those points, which I haven't done, okay? So that is more difficult to track just from this picture. Yes.
This picture does have at least a statistical description of these hierarchy of subhalos in a halo, right?
In principle, yes, there is. Even if you have at that point this halo, you know that there are small halos which have were formed at that places. Yes. It is just that after merger, whether they are retaining their subhalo nature or they have merged to form a bigger halo, that part won't be clear from this picture. I guess that is what you were asking. Yes, I agree. Yeah, that is more difficult to do.
Suppose I'm keeping track of the halo mass function. Let's say I'm plotting a histogram, how many
Yes.
halos of what mass I have
Yes.
at such redshift. Now at smaller redshift, let's say again my two halos have merged, M1 and M2. So how will my histogram change? will I remove the two entries of M1 and M2, have a third entry in M1, or will M1 and M2 also remain and I'll have a third entry at
No, a
M1?
third entry. So in simulation, if you
Delete
do,
the first two
yeah.
entries.
And all this combination will give you a consistent mass function which will evolve. So in simulations, you can also, in simulations, you can track sub-halos. And I think the halo finder you are using won't give you sub-halos. For that, you need like slightly more sophisticated halo finders. And you can do that as well. But when we talk about halos and halo mass functions, what you said is correct. If two halos merge, then from those two bins, you subtract -1 in the histogram, and in some other high mass bin, you add 1. It's just that in simulation, you will be able to track the identity of the particles and really see whether the halos have merged and where they came from, and what kind of halos merged at what redshift. Here, you will only be able to do it statistically in a probabilistic sense.
I don't see any further questions. Let's thank Tirth for this very clear lecture, full of insights.
Thanks.
And we will come back at 11:30 for the tutorials.